One more kind of energy that's worth noting, it equals mc squared. Obviously, I'm sure you remember the German patent clerk that that proved this formula, and that's a pretty big deal. It's a really big deal. So let's go ahead and read page 292 in the book real quick, because they have a good paragraph about it. So energy equals mass times the speed of light squared. That's c is the speed of light, 3 times 10 to the 8 meters per second squared. And so from this, you can see that a little bit of mass stores a large amount of energy, right? Because you're multiplying by a huge number. Okay? And if you're interested, read page 292 about the pole vaulter who bends a pole, and the pole itself actually has then some change in mass. Okay, another really important concept you need to know is conservation of energy. The law of conservation of energy is huge. Okay? It says that in a closed, isolated system, energy can neither be created nor destroyed. Rather, energy is conserved. It's a pretty big deal, especially when you think about that in terms of the cosmos. There is no energy input into the cosmos, which means that eventually all the stars will burn out. That's just a fact. There's no energy input. Eventually all the energy will run out. So mechanical energy is going to be kinetic energy plus potential energy. All right? And the conservation of mechanical energy then is going to be important. And that is, before a collision or before some interaction, we have the kinetic energy plus potential energy equals, and then afterwards, whatever kinetic energy, whatever potential energy is there. So a perfect example would be if you have two cars coming at each other like this, and they collide. All right, the before would be before they collide. So we could find the kinetic energy of both of them before they collide. Then afterwards, it would have to equal the kinetic energy of them if they're like smashed together and moving off together. The original kinetic energy must equal the final kinetic energy. Now there would be no potential in that situation, so I could get rid of that. But basically the energy must be conserved. So the energy of a system beforehand has to equal the energy of the system afterwards. That's the law of conservation of energy. Let's try an example problem then. Let's say during a hurricane, a large tree limb with a mass of 22 kilograms and a height of 13.3 meters above the ground falls on a roof that's 6 meters above the ground. Ignoring the air resistance, find the kinetic energy of the limb when it reaches the roof. So after you draw your picture, you can think about conservation of energy. So we know the energy before, this is what I always write, the energy before has to equal the energy afterwards because that's the law of conservation of energy. So the energy before is all in the form of gravitational potential energy. There's no movement from the limb at first. So it's all gravitational potential energy, which I'll just use potential energy. And then afterwards, the limb is going to strike right here, and it's going to at that point have kinetic energy plus potential energy. So it'll have, it's moving now, but it's still a little bit above the ground. So I'm going to say it has both potential energy and kinetic energy. So the potential energy before is mgh, which in that case is the mass of 22 kilograms times gravity of 9.8 times the height of 13.3. And that's going to equal the potential energy, which is also mgh, but that h is afterwards is smaller. That's at 6 feet now. So that'd be 22 times 9.8 times 6 for its height, plus the kinetic energy, which is what we're going to try to find here. Okay? So all we have to do is subtract this quantity to the other side, and we get the kinetic energy is equal to 1,573.9 joules of kinetic energy when it reaches the house. So if bar B wants to know the speed, well, we know the kinetic energy equals 1/2 mv squared, so we can find out how fast it's going based on that energy. So kinetic energy is 1573.9 joules. That has to equal 1/2 the mass, which is 22 kilograms, times the velocity squared. If I multiply both sides by 2, and then divide both sides by 22, and then square root both sides, that gives me the final velocity of the limb at the roof, 11.96 meters per second at the roof. You could go ahead and double check this with this formula. Velocity final squared equals initial velocity squared plus 2a bar change in distance. This is what we used in the first unit to find out how fast an object was going as it was dropped from rest. And if you did it this way, you get the same answer, 11.96. You can check it with the old method. Now we have a new method. We have a new method called conservation of energy, which is another way to look at things and figure out missing information like how fast something's going when it falls a certain distance. A couple other things that you need to know are elastic collisions and inelastic collisions. Elastic collisions are collisions in which kinetic energy doesn't change. Okay, there's no change in kinetic energy. An inelastic collision is where kinetic energy decreases after the collision. So, an example of an inelastic collision would be you throw like some putty at a wall. Okay, the thing's not going to bounce off with the same speed that it went in at. Most likely, it's going to like kind of hit the wall and drop straight down. And the reason why is because that's an example of inelastic collision where there's some energy given off. So when that clay or that putty hits the wall, it's going to deform shape. It's going to change its shape, and when it does, it basically heats up. So it's going to lose energy through the deformation of those molecules, which then creates heat, because that's what heat is. Heat is the movement of molecules. So an example of an elastic collision would be a bouncy ball hitting a wall. When a bouncy ball hits a wall, it bounces off with a similar speed that it hit the wall with, because it's more elastic. So it doesn't give up, it doesn't deform as much and give off energy. It retains most of its kinetic energy. And that's an elastic collision. That next. Let's try an example though first. In an accident on a slippery road, a compact car with a mass of 575 kilograms moving at a speed of 15 meters per second smashes into a rear end of a car with 1,575 kilograms moving at 5 meters per second in the same direction. What's the final velocity if the wrecked cars locked together? Okay, so we have before and afterwards. Okay, beforehand, we've got one car moving at 15 meters per second, and we've got another car moving at 5 meters per second. So I'll try to draw a picture of this. This will be rough, but we got one car that's traveling at 15 meters per second, and it's got a mass of 575 kilograms. And it's going to hit this other car, which is going slower. This other car has a mass that's bigger of 1,575 kilograms, but it's only moving at 5 meters per second. Okay? So beforehand we have a certain amount of kinetic energy, and afterwards the cars are going to lock together. So I'm just going to draw a big heat there. There's both cars. I'm not going to draw both. I don't know what the final velocity is, but that's what they asked me for. I do know the mass when they lock together though. That's 1,575 plus 575, which is going to be 2,150. All right, so conservation of energy says that before has to equal afterwards. So the energy before has to equal the energy after. So beforehand we have kinetic energy from both of them, which is 1/2 mv squared for the first car, plus 1/2 mv squared for the second car. So this is the first, this is the second car. All right, that's 1/2 575 times 15 squared, plus 1/2 1575 times 5 squared, if you plug in the mass and velocity of both those cars. Now we know that has to equal the energy afterwards, which is 1/2 mv squared, and we know the mass afterwards was 2,150. So it's going to be 1/2 2,150 times the speed afterwards. We can divide both of this by 1/2 and 2,150. And that gives us our, if we take the square root of that anyway, that's going to give us our speed of both cars locked in afterwards, which is, it should be about 8.9 meters per second afterwards. And that makes sense, right? If one's going 15 meters per second, the other one's going 5, it makes sense that they'd meet somewhere in the middle, and closer to the 5 because that car has a little more inertia because it's got more mass. So the last thing we need to talk about is impulse momentum theorem, which it says that the impulse is equal to the change in momentum. Now impulse right here is another thing you're going to need to know. Impulse is on your formula sheet. It's the force that you apply to something times the time interval that you apply that force. Okay, this is the key to understanding basically any collision and how to decrease the transfer of energy during that collision. So it's the impulse momentum theorem right here. It says the impulse is equal to the change in momentum. Okay? So if you want to decrease the change in momentum, when you say your car is swerving out of control and you have the option of hitting a tree or some bushes, you obviously want to hit the bushes. And the reason why is because if you increase the time interval here that you apply the force for, the force will decrease. That's causing you to decelerate. So if you increase the time during collision, you're going to decrease the force that's causing the deceleration. And that's obviously the key right there, is decreasing that. The transfer momentum is going to be the same. Your car was going 50 miles per hour. When you crash, it's going to eventually be going 0. So this momentum is going to be constant. Let's say the change in momentum is going to be 500 joules. I don't know, or 500 newtons. I should say 500 newton seconds would be the right units.
Yeah.
Now, we know that that's 500 newton seconds. So basically, if you can increase the time during the collision, you'll decrease the force that's causing you to decelerate. The last thing then from this chapter you need to know that we're going to use is the formula for potential energy stored in a spring, found by Mr. Hooke. And then also Hooke's law, which is that the force that we apply to change a spring is equal to opposite the coefficient, the spring coefficient, times x. Okay, so the force needed to stretch a spring is equal to the opposite of the spring coefficient, which depends on the spring and the material it's made out of, times the distance that you stretch that spring. So x in this case is the distance of the stretched spring in both cases.